Deep in space, something is breaking the rules we thought were absolute. Astronomers just found black holes eating 40 times faster than physics should allow. These cosmic monsters appeared just 500 million years after the universe began, yet they're already billions of times more massive than they should be. We're about to journey into the most violent feeding frenzies ever witnessed, where gravity bends the very laws we use to understand reality. If you're fascinated by the impossible, hit that subscribe button, take a breath. We're diving into the abyss. Picture a black hole consuming the mass of our entire star every single day. Now multiply that by 40. That's what astronomers discovered when they pointed their instruments at a distant dwarf galaxy. This cosmic glutton sits 1.5 billion light years into the past, feeding at a rate that should be physically impossible. The discovery came from combining data between humanity's most powerful tools. The James Webb Space Telescope spotted the galaxy's faint infrared glow. The Chandra X-ray Observatory detected the scorching radiation pouring from superheated gas spiraling toward doom. Together, they revealed something that makes physicists uncomfortable: a black hole gorging itself at 40 times the theoretical maximum. Think of it like trying to drink from a fire hose. The pressure should blow everything backward. That's essentially what happens near a feeding black hole. Material falling inward gets compressed and heated to millions of degrees. This creates outward pressure that should push away any additional food. The balance between gravity pulling in and pressure pushing out sets a cosmic speed limit. We call it the Eddington limit, named after the British astrophysicist who calculated it nearly a century ago. This black hole ignores that limit completely. It's swallowing gas so fast that powerful winds are screaming outward at thousands of miles per second. Astronomers can see these winds in the spectrum of light, watching matter getting expelled even as more matter plunges inward. The black hole gained most of its mass during this single binge, growing more in one feeding episode than it should in millions of years. This isn't just unusual, this is reality bending. The black hole sits in a small galaxy that shouldn't have enough material to feed such rapid growth. The total mass of gas available seems insufficient for the feast we're witnessing. Yet somehow, dense streams of gas are flowing directly into the center, bypassing the usual delays and obstacles. The environment around this monster is chaotic beyond anything we observe in the modern universe. The numbers tell a shocking story. At normal feeding rates, building a black hole this massive would require hundreds of millions of years of continuous growth. This object appears to have accomplished the same feat in a fraction of that time. The implications cascade outward like ripples in a pond. If one black hole can break the rules this dramatically, how many others have done the same? Scientists realized they were witnessing a missing link. For years, astronomers have puzzled over how supermassive black holes could exist so early in cosmic history. The math simply didn't work using normal growth rates. Either black holes started much bigger than we thought possible, or they found ways to grow much faster. This discovery provides evidence for the second option. These feeding frenzies, though brief and violent, could explain how cosmic runts became galactic giants. The discovery raises an unsettling question. If this black hole can break one fundamental limit, what other rules are being shattered in the depths of space we haven't explored yet? Every black hole faces an invisible barrier built from physics itself. Understanding this wall is crucial to grasping why the recent discoveries are so shocking. When a black hole feeds, the process is violent. Gas and dust spiral inward, forming a disk around the monster. Friction in this disk heats the material to extreme temperatures, often millions of degrees. At these temperatures, matter doesn't just glow, it screams. Radiation pours outward in every direction, carrying energy and momentum. Here's where the wall appears. That outward flowing radiation pushes against the incoming gas. Photons, though massless, carry momentum. When trillions upon trillions of photons slam into gas particles, they create real pressure. Push hard enough, and you can actually reverse the flow. The gas gets blown away instead of falling in. Arthur Eddington figured this out nearly a century ago while studying stars. The same principle applies to black holes. For any given mass, there's a maximum rate at which it can consume matter before its own radiation blows away the food. Cross that threshold and feeding stops. The black hole has effectively put itself on a diet through its own brightness. Scientists can calculate this limit precisely. For a black hole with the mass of 1 million stellar masses, the limit allows it to gain about 20 masses per year. That might sound like a lot. In cosmic terms, it's painfully slow. To grow from a stellar mass black hole weighing 10 times our star to a billion solar mass giant would take hundreds of millions of years at this rate. The early universe simply didn't have that much time. Observations from James Webb show billion solar mass black holes existing when the universe was only 500 million years old. Running the math backward, these monsters would have needed to form almost immediately after the Big Bang and grow at the maximum possible rate every single year. No breaks, no slow periods, constant feeding at the absolute limit for hundreds of millions of years. That scenario seems unlikely. Galaxies weren't orderly in their youth. They crashed together, merged violently, and went through periods where star formation consumed most available gas. Black holes would have faced times of feast and famine. The wall should have held them back, kept them smaller, younger, less developed during any period where food became scarce. Yet, the giants exist. The wall should have been insurmountable. It should have delayed their growth by hundreds of millions of years. Something allowed them to break through. Something let them cheat the system in ways we're only beginning to understand. The Eddington limit isn't just a theoretical curiosity. It's a fundamental constraint woven into the fabric of how matter and light interact. Breaking it requires special conditions, specific geometries, or forces we haven't fully accounted for. The fact that early black holes routinely exceeded this limit tells us the early universe was a very different place. What happens when an unstoppable force meets an immovable object? In this case, the unstoppable force won. The question is, how? The universe has a birthday. 13.8 billion years ago, everything began. We can trace cosmic history backward with remarkable precision, watching galaxies form, stars ignite, and the first light pierce the darkness. The timeline is well established, which makes the supermassive black hole problem so troubling. When astronomers turned James Webb toward the most distant reaches of space, they expected to find young galaxies with modest black holes at their centers. What they found instead were monsters that shouldn't exist yet. Black holes with masses exceeding 1 billion stellar masses, sitting in galaxies formed when the universe was less than 600 million years old. 600 million years sounds like forever. In cosmic terms, it's barely a moment. The first stars needed time to form from clouds of hydrogen and helium. Those stars needed time to live and die. Their deaths would seed space with heavier elements necessary for planet formation and complex chemistry. All of this takes time. Lots of time. The first black holes would have formed from the deaths of massive stars, creating objects perhaps 10 to 100 times our star's mass. These are stellar mass black holes. Growing from 100 to 1 billion means a 10 million-fold increase. Even at the absolute maximum feeding rate allowed by physics, this process should take far longer than 600 million years. Astronomers ran the calculations again and again. The numbers didn't cooperate. To explain what James Webb was seeing, black holes would need to have formed impossibly early, perhaps within the first 100 million years after the Big Bang. Then they would need to feed continuously at or above the maximum rate for the entire remaining time. No gaps, no slow periods, just relentless, perfect growth under ideal conditions for hundreds of millions of years. Reality is never that perfect. Galaxies go through violent mergers that disrupt gas flows. Star formation consumes material that might otherwise feed black holes. Powerful stellar winds from massive young stars and explosive supernovae can blow gas out of galactic centers entirely, sometimes for millions of years. Any of these events would slow black hole growth, creating gaps in their feeding schedule. Even brief interruptions would throw off the timeline significantly. The timeline problem gets worse when we count how many of these early giants exist. James Webb hasn't found just one or two anomalies. It's found dozens. That means the rapid growth process, however it worked, wasn't rare. It was common in the early universe. Something fundamental about those early cosmic conditions enabled black holes to grow faster than physics textbooks said they could. Either our understanding of black hole formation is incomplete, or the early universe operated under different rules than today. Scientists started exploring both possibilities, knowing the answer would reshape our understanding of cosmic evolution. The evidence was mounting that something extraordinary happened in the universe's youth. The clock was ticking from the very beginning. These black holes somehow won a race they should have lost by a landslide. Imagine weighing something that has no surface, just gravity so intense that even light cannot escape. That's the challenge of measuring black holes. Yet astronomers have developed clever techniques, and the results from the early universe are staggering. One method involves watching stars orbit the black hole. Just as planets reveal stellar mass through their orbital speeds, stars circling a galactic center betray the mass of the central monster. Another technique examines the motion of glowing gas near the black hole, measuring how fast it swirls before plunging inward. When scientists applied these methods to early galaxies, the numbers made them double-check their calculations. A galaxy observed from 12 billion years in the past contained a black hole weighing 19 billion stellar masses. Another early galaxy hosted a monster exceeding 10 billion. These weren't exceptions. They were part of a pattern. The sheer weight creates problems beyond just the timeline. Mass doesn't appear from nowhere. Every bit came from somewhere. Gas clouds, stars, perhaps smaller black holes that merged together. In the modern universe, we can account for where black holes get their food. Early galaxies were different. They were smaller, less mature, still forming their first generations of stars. The total amount of material available was limited. Some of these early supermassive black holes outweigh all the stars in their host galaxies combined. The black hole became more massive than the entire stellar population meant to feed it. This creates a paradox. If a black hole grows by consuming material from its galaxy, how can it end up heavier than the galaxy itself? Something about the relationship between black holes and galaxies was fundamentally different in the early universe. The black holes weren't just passengers, they were dominant forces. One galaxy discovered by James Webb exemplifies this weirdness. The galaxy existed just 570 million years after the Big Bang. Its black hole is overmassive compared to the galaxy's stars. In the modern universe, there's a predictable relationship between black hole mass and galaxy mass. This early system violates that relationship completely. The discovery suggests black holes in the early universe grew at an accelerated pace even in relatively small galaxies. They didn't wait for their host galaxies to mature. They raced ahead. This challenges our understanding of how galaxies and black holes co-evolve. The impossible weight of these early black holes points to processes we don't yet understand, mechanisms that allowed rapid mass accumulation despite all the obstacles. Time is the ultimate constraint in physics. You cannot skip ahead. Events must unfold in sequence. When astronomers map cosmic history, they're creating a timeline of what could have happened when. For supermassive black holes in the early universe, that timeline has missing years. Consider a black hole weighing 1 billion stellar masses at cosmic age 600 million years. Working backward, we need to account for every stage of growth. First, a seed black hole must form. Let's say this happens when the universe is 100 million years old, giving us a stellar mass black hole weighing 100 times our star. At the theoretical limit, this black hole could roughly double its mass every 50 million years. Sounds fast, but do the math. After 50 million years, it weighs 200 stellar masses. After 100 million years, 400, you need about 20 doubling periods to reach 1 billion. 20 doublings times 50 million years each equals 1,000 million years total. We only have 500 million years available, the missing years number in the hundreds of millions. Half the required time simply doesn't exist in the cosmic timeline. Scientists explored various workarounds. Maybe the seed black holes started much larger than we thought. Instead of 100 stellar masses, perhaps they formed with 100,000 right from the start. This helps, creating its own problems. How do you form such massive seeds without going through normal stellar evolution? Another possibility involves growth rates exceeding the theoretical limit. If black holes could temporarily feed faster than the maximum, they could compress their growth into shorter time spans. Think of it like cramming for an exam. The problem is that super-fast growth was thought to be rare and short-lived. Some theorists proposed that black holes might have formed before the first stars during an even earlier phase. These primordial black holes would give themselves a head start, more time to grow. However, this requires new physics beyond our standard models. The missing years point to a gap in our knowledge. Something happened in the early universe that our current theories don't capture. Whether it's a new formation mechanism, a way to exceed growth limits, or conditions that made feeding much more efficient, the explanation must be dramatic. Every attempt to solve the timeline problem reveals another layer of complexity. The universe was doing something in its youth that it doesn't do anymore. November marked a turning point. Astronomers announced findings that would fundamentally challenge our models of black hole formation. The discovery came from a galaxy so distant its light traveled for 12 billion years before reaching our instruments. What they found wasn't just unexpected, it was impossible according to existing theory. The James Webb Space Telescope made the initial detection. Among thousands of objects in Chandra's catalogue, this galaxy stood out. It blazed brilliantly in X-ray light, while remaining nearly invisible in optical wavelengths. This combination suggested something extreme was happening at its core. Webb's infrared sensitivity could pierce through dust and distance to see what optical telescopes missed. The spectrum told the story. When astronomers spread the galaxy's light into its component colors, they saw signs of gas moving at thousands of miles per second. This wasn't random motion. The gas showed a specific pattern, swirling in a disk around a central mass. The speeds were so high that only a supermassive black hole could generate them. Then came the X-ray data. The intensity and characteristics of the X-ray emission allowed astronomers to estimate how fast the black hole was consuming matter. They ran the calculations multiple times, certain they had made an error. The accretion rate came out to 40 times the theoretical maximum. They checked their instruments. They verified their methods. The number didn't change. This single measurement changed the conversation. Scientists had theorized about superfast accretion before. Observations were rare and disputed. Some researchers questioned whether the earlier detections were real or artifacts of measurement errors. This provided clear, unambiguous evidence that black holes could exceed their theoretical feeding limit by enormous factors. More importantly, they could sustain this extreme behavior long enough to have observable effects on their growth and evolution. The discovery validated decades of speculation. If black holes in the early universe could feed this rapidly, even for brief periods, it would solve the timeline problem. A black hole growing at 40 times the normal maximum could compress millions of years of growth into a much shorter span. Those missing years were found through compression rather than extension. What made the discovery even more significant was the outflow signature. Webb detected powerful winds streaming away from the black hole, carrying mass at incredible velocities. This material wasn't falling in. It was being ejected. Yet, Despite losing matter to these winds, the black hole continued to gain mass at extraordinary rates. The inflow exceeded the outflow by a massive margin. Astronomers realized they were watching a feeding frenzy in action. This wasn't steady, controlled growth. This was a cosmic feeding burst, a temporary phase where conditions aligned to allow rapid mass accumulation. The black hole was making up for lost time, gorging itself while the opportunity lasted. The discovery opened a new chapter. If this black hole could do this, others could too. The question shifted from whether super-fast growth was possible to how common these feeding frenzies actually were in the early universe. Let's get personal with this monster. It isn't just a catalogue number. It's a window into cosmic extremes, a black hole caught breaking every rule we thought governed its behavior. The black hole sits at the center of a dwarf galaxy, a relatively small collection of stars and gas. Dwarf galaxies are the cosmic underdogs, containing far fewer stars than grand spirals. Their central black holes typically weigh millions rather than billions of stellar masses. They're lightweights. This black hole weighs in at a level inappropriate for its home. The mass ratio between the black hole and its galaxy violates the normal relationship observed throughout the modern universe. It's as if the black hole forgot it was supposed to match its surroundings and instead grew to match much larger galaxies. The feeding mechanism appears tied to the galaxy's chaotic environment. The dwarf galaxy is messy, with clumps of dense gas distributed unevenly throughout its volume. These clumps are cold, their temperatures low enough that they can hold together against pressure. When gravity channels these clumps toward the galactic center, they deliver concentrated streams of fuel directly to the black hole. Think of it like drinking water from a glass versus drinking from a concentrated stream. The black hole isn't sipping gas from a thin, diffuse cloud. It's receiving dense rivers of material flowing straight into its gravitational well. The density makes all the difference. Observations show the black hole accreting matter in a geometrically thick structure rather than a thin disk. This configuration changes how radiation interacts with the infalling material. In a thin disk, radiation can escape relatively easily. In a thick, bloated flow, radiation gets trapped deeper within the structure. The winds streaming away carry heavy elements like carbon, nitrogen, and silicon. We can identify these elements from their spectral signatures. The presence of heavy elements tells us the black hole is consuming gas enriched by previous generations of stars. What's fascinating is the speed of these outflows. Some material is being accelerated to a significant fraction of light speed before escaping. This requires enormous energy input. Yet even with this massive energy expenditure, the black hole continues to gain mass rapidly. Scientists estimate that a substantial fraction of the black hole's total mass was gained during this single extreme episode. Rather than growing slowly over millions of years, it may have doubled or tripled its mass in a cosmic flash. These feeding bursts, though temporary, could be the secret ingredient that explains early supermassive black holes. This represents a new class of object, a system caught mid-transformation, showing us what the universe looked like when black holes were still building their empires. How do you build a monster from a minnow? That's the light seed problem in a nutshell. Scientists long believed that supermassive black holes started from stellar mass seeds, the remnants of the first generation of stars weighing perhaps 10 to a few hundred times our star's mass. The first stars in the universe were different from stars today. They formed from pure hydrogen and helium. Without elements like carbon and oxygen, the gas couldn't cool as efficiently. This led to the formation of truly massive stars, perhaps 100 to 300 times our star's mass. These stellar mass black holes are what we call light seeds. They're light compared to supermassive black holes. The question has always been whether these light seeds could grow fast enough to explain what we observe. Recent simulations say yes, under specific conditions. Researchers at Maynooth University ran sophisticated computer models that followed the evolution of early galaxies in unprecedented detail. they tracked the flow of gas on scales smaller than star clusters. What they found was remarkable. In the chaotic conditions of early galaxies, light-seed black holes could experience explosive growth bursts. These weren't gradual processes. They were feeding frenzies lasting only a few million years. During these bursts, dense clumps of cold gas would flow directly toward the black hole. The key is the gas distribution. Early galaxies weren't smooth and orderly. They were lumpy, with regions of high and low density scattered throughout. When gravity managed to channel one of these dense clumps toward a black hole, the result was a temporary feeding spike. These bursts couldn't last forever. Eventually, the dense gas would be consumed, or stellar explosions would disrupt the flow. The feeding would slow to normal levels, or stop entirely. During those few million years of rapid accretion, the black hole could multiply its mass several times over. Multiple bursts over the early universe's history could bridge the gap. A black hole might go through 3, 4, or even 5 major feeding episodes, each separated by quieter periods. String enough of these together, and you can get from a light seed to a billion solar mass giant. The simulations show this process working for small seeds, removing the need to invoke exotic formation mechanisms. You don't need mysterious heavy seeds or primordial black holes formed before the first stars. Regular stellar mass black holes, given the right conditions, can grow spectacularly fast. However, there's a catch. Only a minority of light seeds actually achieve this rapid growth. Most remain small. This means the early universe should contain many small black holes for every giant. The light seed solution is elegant because it requires no new physics, just extreme versions of processes we already understand. The heavy seed alternity. What if the universe took a shortcut? Instead of slowly building black holes from stellar remnants, perhaps it created massive seeds directly from gas clouds. This is the heavy seed hypothesis. In the very early universe, conditions existed that we never see today. Gas clouds could grow enormous without fragmenting into stars. The key is preventing cooling. When gas cools, it condenses into smaller clumps that eventually become individual stars. If you can keep the gas hot, it stays in a large, diffuse cloud. One mechanism involves intense radiation from nearby galaxies. If a young galaxy is bathed in ultraviolet light from its neighbors, that radiation can keep the gas ionized and hot. This radiation doesn't have enough energy to completely strip electrons from atoms, enough to prevent molecules from forming. Without molecules, the gas can't cool efficiently. It stays hot and diffuse. As gravity tries to pull it together, pressure resists. The cloud reaches a stalemate. Gravity eventually wins. When it does, the entire cloud collapses at once, potentially forming a supermassive star tens of thousands of times our star's mass. These supermassive stars wouldn't live long. They'd burn through their fuel in perhaps 1 million years or less. When they die, they wouldn't explode as supernovae. Instead, they'd collapse directly into black holes, creating seeds weighing tens of thousands or even hundreds of thousands of stellar masses. Starting from 100,000 stellar masses instead of 100 changes the math dramatically. You only need a 10,000-fold increase to reach 1 billion, not a 10 million-fold increase. That's achievable through normal growth within the available time. The heavy seed scenario solves the timeline problem elegantly. However, it requires special conditions that might not have been common. You need the right balance of radiation to prevent cooling without blowing the gas cloud apart entirely. Recent theoretical work suggests another path to heavy seeds through direct collapse of dark matter structures. In this scenario, dark matter halos in the early universe could have captured enormous amounts of gas. The dark matter's gravity would hold the gas together even as it heated up. Observational evidence for heavy seeds is indirect. Some early galaxies show black holes that are overmassive compared to their stars, suggesting the black holes formed before significant stellar populations developed. This fits the heavy seed picture. The discovery of triple black hole systems also supports direct collapse scenarios. In these systems, a black hole is orbited by companion stars. Normal black hole formation from stellar collapse typically can't produce such configurations. Direct collapse from a gas cloud, however, could naturally create a central black hole with companion stars. Whether light seeds or heavy seeds dominated the early universe remains an open question. The answer probably involves both pathways operating under different conditions. The early universe was nothing like the cosmos we see today. It was a maelstrom of colliding gas clouds, merging protogalaxies, and turbulent flows. This chaos wasn't a bug. It was a feature that enabled rapid black hole growth. When we look at galaxies in the modern universe, we see relatively organized structures. Spiral galaxies have neat arms. Elliptical galaxies show smooth distributions. Even irregular galaxies display some level of order. The early universe had none of this. Gravity pulled matter together in clumps of all sizes. Small clumps merged into larger ones. Those larger clumps collided and merged again. Each collision sent shock waves through the gas, compressing it, heating it, and setting up complex flows. This turbulence actually helped black holes grow. In a calm, stable galaxy, gas settles into orderly rotation far from the center. Getting that gas to fall inward requires removing its angular momentum, the rotational energy that keeps it orbiting. This normally takes time. In chaotic early galaxies, angular momentum was constantly being redistributed. Collisions between gas clumps could cancel out orbital motions, allowing material to plunge toward the center more directly. Turbulent flows created instabilities that broke gas into smaller clumps, and some of those clumps had orbits that took them straight toward the central black hole. Computer simulations show that early galaxies had much higher gas densities in their cores compared to modern galaxies. The gas hadn't been consumed by star formation yet. It hadn't been blown out by supernova explosions. It was just sitting there, available for accretion. The turbulence also affected how radiation pressure interacted with infalling gas. In a smooth, orderly flow, radiation can efficiently push gas away. In a chaotic flow with clumps and filaments, some material is shielded from radiation by denser regions in front of it. Temperature variations added another layer of complexity. The early universe contained pockets of extremely cold gas alongside regions heated by young stars and supernovae. Cold gas is dense and clumpy, perfect for feeding black holes. The chaotic mixing created situations where cold, dense streams could form and flow directly to galactic centers. All of these factors combined to create what scientists call a feeding-friendly environment. Black holes didn't have to work hard to find food. The food was delivered to them by the natural turbulence of galaxy formation. As galaxies matured and settled down, these favorable conditions disappeared. The chaos of youth made all the difference. Deep within chaotic early galaxies, astronomers discovered something extraordinary through computer simulations. Rivers of gas flowing through space like cosmic highways, carrying material directly to hungry black holes. In modern galaxies, gas moves in relatively organized patterns. It orbits in disks, spirals slowly inward, and takes millions of years to migrate from the outer regions to the center. Early galaxies threw this rulebook away. High-resolution simulations revealed the structure of these gas flows. Instead of smooth, continuous matter, the early universe had gas organized into filaments and clumps. Imagine looking at a cosmic web with dense threads connecting regions of emptiness. Along these threads, gas could flow rapidly over vast distances. When one of these filaments intersected a young galaxy, it created a direct pipeline to the galactic center. Gas would pour in from intergalactic space, channeled by gravity along the densest paths. The flow could deliver millions of stellar masses of material in just a few million years. The density of these streams matters enormously. Gas flowing in a diffuse cloud faces resistance from radiation pressure and thermal pressure. Gas flowing in a dense filament can overcome these obstacles through sheer mass. The outer layers might get blown away. The core of the stream continues flowing inward. Simulations showed that the density in these streams could exceed 10,000 particles per cubic centimeter. That might not sound like much. In the near vacuum of space, it's extraordinary. The gas between stars in modern galaxies typically has densities of less than 1 particle per cubic centimeter. This density amplification came from gravitational instabilities. As gas flowed along filaments, gravity would compress certain regions, creating denser knots. These knots would then attract more material, growing denser still. By the time the gas reached the galactic center, it had condensed into extremely compact clumps. Temperature played a crucial role. Cold gas is denser than hot gas at the same pressure. The streams feeding early black holes were remarkably cold, sometimes just a few dozen degrees above absolute zero. This coldness allowed the gas to compress to incredible densities. Scientists realized these dense gas rivers solved another puzzle. In normal circumstances, getting gas to fall all the way into a black hole is difficult. The gas wants to settle into a stable orbit. These dense streams had so much momentum and so little thermal support that they couldn't settle into orbit. They just crashed straight into the accretion flow. The duration of these feeding events was limited. Eventually, the filament would shift, redirect, or run out of gas. Star formation would consume some of the inflowing material. While the river flowed, the black hole could feed at extreme rates. Observations from James Webb are starting to confirm these predictions. Some early galaxies show elongated structures pointing toward their centers, possibly these gas filaments caught in the act. These cosmic rivers weren't rare accidents. They were a natural consequence of how structure formed in the early universe. For decades, scientists treated the theoretical limit as an absolute barrier. Black holes couldn't exceed it for extended periods. Recent discoveries proved that assumption wrong and revealed a window in cosmic history when the rules relaxed. The limit exists because of radiation pressure. Feed a black hole too fast, and the intense radiation from heated gas will blow away incoming material. This creates a self-regulating system. That's the theory. Reality in the early universe proved more complex. Super-fast accretion becomes possible when the geometry of the inflowing material changes. Instead of a thin, flat disk where radiation can escape easily from the surface, imagine a thick, bloated flow where radiation gets trapped inside. Photons trying to escape get scattered by dense gas, bouncing around inside the structure. Think of it like trying to leave a crowded stadium. If everyone moves in an orderly line, exit is efficient. If the crowd is chaotic and people keep bumping into each other, progress slows dramatically. Photons in a thick accretion flow face the chaotic crowd problem. The early universe provided ideal conditions for thick accretion flows. The high gas densities and rapid inflow rates naturally created bloated structures around black holes. Instead of thin, elegant disks, these black holes were surrounded by turbulent, puffy tori of gas. Another factor involves magnetic fields. Strong magnetic fields can help channel gas inward while simultaneously allowing radiation to escape along specific directions. The radiation escapes along the magnetic poles while gas continues flowing in along the equator. Recent simulations incorporating magnetic fields show black holes reaching accretion rates up to 10 times the limit sustainably. Add in the geometric effects of thick flows, and rates of 20 to 40 times the limit become achievable for short periods. The super-fast window wasn't open forever. As galaxies matured, gas densities decreased. The chaotic flows that created thick accretion geometries became rarer. The special conditions that enabled extreme feeding gradually disappeared. This window existed roughly between cosmic ages of a few 100 million years to about 1 billion years after the Big Bang. During this period, black holes had access to conditions that would never be replicated. Scientists estimate that a black hole experiencing extreme accretion at 40 times the limit could double its mass in just 1 million years instead of 50 million years. This 50-fold acceleration changes everything about the timeline problem. The discovery that this window existed and was relatively common reshapes our understanding. The early universe wasn't just younger. It operated under fundamentally different conditions that allowed processes impossible in the modern cosmos. When a black hole feeds at extreme rates, existing models predicted the X-ray emission should dim or disappear entirely. The discovery of bright X-ray sources in rapidly feeding early black holes created a paradox. X-rays from black holes come from the corona, a region of extremely hot gas hovering just above the accretion disk. Temperatures in the corona reach hundreds of millions of degrees. At these temperatures, electrons move at significant fractions of light speed. The paradox emerges from basic physics. During extreme accretion, the intense radiation pressure should blow away the corona or cool it down. Without a hot corona, X-ray emission should plummet. Early black holes should be dim in X-rays. Observations showed the opposite. The quasar discovered by Japanese astronomers was shining brilliantly in X-rays, while simultaneously accreting at 13 times the limit. Another showed strong X-ray emission, while feeding at 40 times the limit. These weren't dim sources, these were blazing beacons. Something about the corona's structure, or energy source, must be different during extreme phases. One possibility involves magnetic fields. If powerful magnetic fields permeate the accretion flow, they could provide an energy source to maintain the corona even when radiation pressure tries to blow it away. Another explanation involves the geometry of the accretion flow. If the flow is thick and turbulent rather than thin and smooth, pockets of extremely hot gas could exist deep within the structure, shielded from the outward radiation pressure. The X-ray spectrum itself provides clues. Astronomers don't just measure the total X-ray brightness. They examine how that brightness is distributed across different X-ray energies. The spectrum from extreme black holes shows features that indicate complex absorption and scattering. This suggests the corona exists partially obscured by inflowing gas. We're seeing X-rays that manage to escape a chaotic environment. The paradox partially resolves when we account for this complexity. The persistence of X-ray emission has practical implications. It means astronomers can use X-ray observations to find rapidly feeding black holes in the early universe. If extreme accretion made black holes X-ray dim, we'd miss them entirely. Each X-ray photon carries information about the extreme environment near these black holes. By carefully analyzing the X-ray spectra, scientists can map out temperatures, densities, and velocities in the corona and accretion flow. The X-ray paradox remains partially unsolved. We know the corona survives when theory says it shouldn't. We have ideas about why. Confirming those ideas requires more observations. Black holes don't just swallow matter. Sometimes they launch it back into space at nearly light speed through jets of plasma. The discovery of powerful radio jets from extreme black holes contradicted decades of theoretical work. Radio jets are among the most energetic phenomena in the universe. They extend for hundreds of thousands of light years, carrying energy equivalent to trillions of stars. The jets emit radio waves due to electrons spiraling around magnetic field lines at relativistic speeds. Creating a jet requires specific conditions near the black hole. Most theories involve magnetic fields threading through the accretion disk. As the disk rotates, it twists these magnetic fields into tight helices. Energy builds up until it gets channeled outward along the rotation axis. The problem is that extreme accretion should disrupt this process. When a black hole feeds too rapidly, the accretion disk becomes bloated and turbulent. The organized rotation that twists magnetic fields should break down. Jets should weaken or disappear. Yet, the quasar studied by researchers showed strong radio emission indicating a powerful jet. The black hole was simultaneously accreting at 13 times the limit, shining brightly in X-rays, and launching a relativistic jet, all three phenomena at once. Radio emission requires a sustained jet. Brief, flickering outflows wouldn't produce the observed radio brightness. The jet had to be stable over timescales of thousands to millions of years during extreme feeding. Magnetic fields might again provide the answer. If the black hole itself possesses a strong magnetic field, that field could remain organized even when the surrounding matter becomes turbulent. The black hole's rotation would twist its own magnetic field into a jet. This requires the black hole to be spinning rapidly. A slowly rotating black hole can't generate strong jets. Observations suggest many early supermassive black holes are indeed spinning near their maximum possible rates. Another possibility involves the jet being powered by the extreme accretion itself. The excess energy that can't radiate away efficiently might get channeled into jet formation. Instead of the jet being a separate phenomenon, it becomes a pressure relief valve. The jets from extreme black holes might be different from jets produced by normal accretion. They could be wider, more turbulent, or variable on shorter timescales. Next-generation radio telescopes might reveal structural differences. What's certain is that these jets exist and are energetic. They're punching through the surrounding gas, creating bubbles of hot plasma that can extend across the entire host galaxy. The radio jet contradiction highlights how much we still don't understand about black hole physics. In the constellation of Hydra, 12 billion light-years from Earth, sits a quasar that shouldn't function the way it does. Astronomers measured its feeding rate at 13 times the limit, while it simultaneously displayed features that theory said should vanish. The discovery began with X-ray observations showing an unusually bright source. When researchers followed up with the Subaru telescope in Hawaii, they used the near-infrared spectrograph to measure the motion of gas near the black hole. From that velocity, they calculated the black hole's mass. The mass came in at a few 100 million stellar masses. Then they estimated the accretion rate using the X-ray luminosity. The numbers didn't make sense initially. The black hole appeared to be consuming matter 13 times faster than radiation pressure should allow. Triple checking confirmed the result. This wasn't measurement error. The quasar was genuinely violating the limit by a factor of 13. More remarkably, it was doing so while producing copious X-rays and driving a powerful radio jet. What makes this quasar special isn't just the high accretion rate. Plenty of objects have been proposed to exceed the limit by factors of 2 or 3. 13 is extraordinary. It suggests conditions near the black hole are radically different from anything we observe in the modern universe. The implications are profound. If a black hole can sustain 13 times limit accretion while maintaining a corona and jet, the growth timescales shrink dramatically. A black hole growing at this rate could increase its mass tenfold in roughly 50 million years instead of 500 million years. Scientists began searching for other objects showing similar characteristics. If this quasar is unique, it might be a rare fluke. If many early quasars show extreme accretion rates of 10 or more times the limit, it indicates a common phase. Early results suggest these extreme feeders are rare. Among the dozens of early quasars studied in detail, perhaps 1 in 10 shows clear signs of accretion rates exceeding 5 times the limit. The 13 times case remains on the extreme end. This suggests a spectrum of feeding behaviors. Some black holes access conditions that allow moderate extreme accretion, growing at 2 to 5 times the limit. A smaller subset finds itself in especially favorable circumstances, achieving rates of 10 times or higher. The duration of this extreme feeding phase remains uncertain. It could last a few million years, or it might be a brief burst lasting only hundreds of thousands of years. Even a short episode at 13 times the limit would dramatically increase the black hole's mass. What triggers such extreme episodes? The answer likely involves a perfect storm of conditions: dense gas flows, favorable magnetic field geometry, rapid black hole spin, and perhaps just the right amount of turbulence. All of these factors must align. The 13 times violation represents the cutting edge of our observations. It's pushing the boundaries of what we thought possible. The corona is a mysterious region. We can't see it directly, can't image its structure, can't probe it with spacecraft. We know it exists only through the X-rays it produces. During extreme accretion, this invisible structure faces forces that should tear it apart, yet it endures. Understanding why requires diving into the physics of extremely hot plasma. The corona contains electrons moving at significant fractions of light speed. These electrons have temperatures exceeding 100 million degrees, far hotter than the accretion disk below them. Where does this heat come from? One source is magnetic reconnection. Magnetic field lines threading through the accretion disk get twisted and tangled by the rotating gas. When these tangled fields suddenly reconnect and snap into simpler configurations, they release enormous energy. Another heat source involves shocks and turbulence. As gas spirals inward, it doesn't move smoothly. Instabilities create shock waves where gas collides at high velocities. These shocks heat small regions to extreme temperatures. During extreme accretion, both heating mechanisms face challenges. The intense radiation pressure should blow away any hot gas trying to form a corona. Magnetic fields get stretched and disrupted by the rapid, chaotic accretion flow. Yet observations show coronae surviving and even thriving. The X-ray spectra indicate temperatures and densities consistent with healthy coronae producing copious high-energy photons. Something is shielding these regions or providing additional energy. One possibility involves magnetic field strength. If the magnetic fields near the black hole are extremely powerful, they could confine the corona even against strong radiation pressure. The field acts like a magnetic bottle, holding the hot plasma in place. Simulations incorporating strong magnetic fields show coronae that are more compact and denser than in normal accretion scenarios. Instead of a diffuse halo above the disk, the corona might exist as dense knots along field lines. Another factor involves the black hole's spin. Rapidly spinning black holes drag spacetime around with them. This affects the behavior of magnetic fields and plasma near the event horizon. The dragging motion could provide additional energy to the corona. The geometry of the accretion flow also matters. If gas is falling inward along specific channels rather than in a uniform disk, the corona might occupy the regions between these channels. It would be partially shielded from the densest inflows. Evidence for this channeled inflow comes from variability studies. X-ray brightness from these black holes fluctuates on timescales of hours to days. These fluctuations suggest clumpy, non-uniform accretion. The survival of coronae during extreme accretion has become a key observational constraint. Any successful model must explain how coronae persist and remain hot enough to produce the observed X-ray emission. This persistence might be telling us that our understanding of radiation pressure in extreme environments is incomplete. Magnetic fields permeate the cosmos, shaping phenomena from planetary magnetospheres to galaxy clusters. Recent work suggests they might be the key to unlocking how black holes grow beyond normal limits. The early universe's first stars generated magnetic fields through dynamo processes. As these stars died and formed black holes, some of their magnetic field likely survived. More importantly, the gas flowing toward black holes carried its own magnetic fields. When magnetic fields get compressed, they strengthen. As gas falls toward a black hole, it gets squeezed into increasingly smaller volumes. This compression amplifies any embedded magnetic fields by factors of millions or billions. New simulations by researchers incorporated magnetic fields into their models of early black hole growth. The results were striking. magnetic fields allowed black holes to grow to masses that would be impossible without them. First, they helped funnel gas directly toward the black hole. Magnetic field lines act like rails, channeling ionized gas along specific paths. Gas moving along field lines experiences less resistance than gas trying to move across them. Second, magnetic fields help remove angular momentum from inflowing gas. This is crucial because angular momentum normally prevents gas from falling straight into the black hole. Magnetic stresses can transport angular momentum outward while allowing matter to flow inward. Third, powerful magnetic fields can eject matter from the system through jets and winds. This might seem counterproductive. By removing some material with high angular momentum, the magnetic ejection allows the remaining gas to fall inward more easily. The simulations showed that black holes embedded in strong magnetic fields could sustain extreme accretion rates for extended periods. The magnetic field geometry allowed radiation to escape along certain directions while gas continued flowing in along others. Observations are beginning to test these predictions. The polarization of light from early quasars can reveal information about magnetic field structure. Polarized light gets its orientation from interactions with magnetic fields. Early results show that young quasars often have highly organized magnetic field structures, consistent with the idea that strong fields played a crucial role. The fields aren't random or chaotic. They show large-scale organization extending across the inner accretion region. The magnetic field strength near these early black holes might reach thousands or even millions of times stronger than fields around modern supermassive black holes. These intense fields result from the high densities and rapid compression of gas. One particularly interesting prediction involves how magnetic fields affect black hole spin. If fields preferentially channel gas from specific directions, they could spin up black holes to near maximum rotation rates. Rapid spin then helps launch jets more efficiently. Future observations with advanced telescopes will test the magnetic field theory more rigorously. Measuring field strengths directly in distant quasars remains challenging. New techniques are making it possible. If magnetic fields are indeed the key, it explains why extreme growth was common in the early universe. For years, computer simulations of black hole growth produced results that didn't match observations. Black holes in simulations grew too slowly. Early galaxies in simulations had black holes too small. Then researchers changed their approach. The problem was resolution. Previous simulations couldn't follow gas on small enough scales. They modeled galaxies in chunks hundreds of light years across. That's fine for seeing overall galaxy evolution. It misses the crucial details near black holes. Attempting to simulate both scales simultaneously requires enormous computational power. You'd need to track trillions of resolution elements. Until recently, such calculations exceeded available computing resources. The Maynooth University team used a clever technique called adaptive mesh refinement. The simulation starts with relatively coarse resolution across the entire galaxy. When it detects interesting features like dense gas clumps, it automatically refines the grid in those regions. This approach allowed them to resolve structures just a few trillion miles across inside galaxies, spanning hundreds of thousands of light years. The resolution jump was enormous. What they saw at these fine scales changed everything. Dense gas clumps appeared that previous simulations had blurred away. These clumps could survive the journey from the outer galaxy to the central black hole. When they arrived, they delivered concentrated bursts of fuel that triggered rapid accretion episodes. Between these bursts, the black holes grew slowly or stopped entirely. This episodic growth pattern matched what observations were showing. Rapid accretion isn't constant. It's bursty, with quiet periods separating active episodes. The new simulations also captured the chaotic nature of early galaxy gas dynamics. Turbulence, shocks, and instabilities created conditions where gas could lose angular momentum rapidly. Some gas clumps ended up on nearly radial orbits, plunging straight toward the center, Running these high-resolution simulations required months of computation on powerful supercomputers. A single galaxy simulation might use millions of processor hours. The researchers ran dozens to explore different initial conditions. The results were remarkably consistent. Light-seed black holes, starting from just 100 stellar masses, could grow to 10,000 stellar masses within a few 100 million years through episodic extreme accretion. Some simulations produced even more extreme growth. The simulations made specific predictions testable with observations. They predicted that rapidly growing black holes should show variability on short timescales as gas clumps fall in. They predicted strong outflows coexisting with rapid inflows. All of these predictions appear consistent with what James Webb and Chandra are finding. The simulation breakthrough didn't require new physics. It just required modeling the known physics at sufficient resolution. The success has transformed the field, giving scientists confidence that they understand the basic mechanisms of rapid black hole growth. Growth in the early universe wasn't steady. It came in bursts. This realization fundamentally changed how scientists think about supermassive black hole formation and evolution. The burst pattern emerged from both simulations and observations. Simulations showed black holes experiencing brief episodes of rapid accretion separated by long, quiet periods. Observations revealed black holes that appeared overly bright for their estimated long-term average feeding rate. Think of it like eating. You don't consume food continuously. You eat meals separated by hours of digestion. Black holes in the early universe followed a similar pattern. Their meals were violent affairs lasting millions of years. What triggers a burst? The arrival of dense gas at the galactic center. In the chaotic conditions of early galaxies, gas distribution was clumpy and irregular. Sometimes, gravity would channel a massive clump toward the center. Other times, the central region would be relatively empty. When a dense clump arrived, it triggered rapid accretion. The black hole couldn't consume the gas instantaneously. The feeding process took time. During that time, the accretion rate could far exceed the limit. The burst would continue until the gas clump was exhausted. Stellar feedback refers to energy and momentum injected by stars. Massive stars produce powerful winds. When they die as supernovae, they release enormous energy that can heat and blow away surrounding gas. A supernova exploding near the galactic center could abruptly terminate the black hole's meal. The duration of feeding bursts varied. Some might last only a few 100,000 years. Others could persist for 10 million years or more if the gas supply remained sufficient. The average burst duration appears to be a few million years based on simulations. Between bursts, black holes would grow slowly, if at all. The galactic center might lack dense gas after the previous burst consumed it. Star formation might be consuming most available gas. The black hole enters a quiescent phase, waiting for the next delivery. This episodic pattern solves several puzzles. It explains why we see some early black holes that appear extremely bright and rapidly growing while others of similar age are much dimmer. We're catching them at different phases of their feeding cycle. The pattern has implications for black hole spin evolution. During a burst, the black hole preferentially accretes gas from one direction, which tends to spin it up. Between bursts, the spin might decay slightly. Multiple bursts from similar directions could spin black holes up to near their maximum possible rotation rates. High spin enables more efficient jet launching, which creates a feedback loop. Rapidly spinning black holes produce powerful jets during feeding bursts. These jets can regulate subsequent star formation, affecting how much gas remains available for future bursts. Observationally, testing the burst pattern is challenging. We see each galaxy at only one moment in cosmic time, a snapshot. Determining whether a black hole is in a burst or between bursts requires comparing many objects at different stages. James Webb's large surveys are starting to enable such statistical studies. By analyzing hundreds of early black holes, astronomers can reconstruct the typical feeding pattern. The burst pattern represents a paradigm shift from thinking about steady growth to recognizing the episodic nature. In a galaxy 600 million light-years away, astronomers discovered something unprecedented: a supermassive black hole racing through space at over 2 million miles per hour, plowing through its home galaxy. The discovery came from James Webb. Researchers were studying early galaxies when they noticed something odd about one particular object. The spectral signatures indicated motion, organized rotation of a stable galaxy. This was linear motion, a galaxy with its central black hole displaced from where it should be. Follow-up observations confirmed the bizarre scenario. The black hole wasn't sitting peacefully at the galactic center. It was offset by thousands of light-years, moving through the galaxy's stellar population at incredible velocity. We're witnessing a runaway black hole. What could launch a 1 million solar mass black hole to such speeds? The most likely explanation involves a three-body interaction. Imagine two supermassive black holes orbiting each other at a galaxy's center. If a third massive black hole enters the system, the gravitational dynamics become chaotic. In such three-body interactions, one object often gets ejected at high velocity while the other two draw closer together. If this happened in the observed galaxy, we're seeing the aftermath. The velocity is staggering. At 2 million miles per hour, the black hole could travel from Earth to our moon in just 7 minutes. On galactic scales, it will traverse the entire galaxy in just a few 100 million years. As the runaway black hole plows through gas clouds in the galaxy, it triggers star formation in its wake. The black hole's gravity and the shock wave from its passage compress gas, causing it to collapse and form new stars. Observations show a trail of young stars behind the moving black hole. This discovery has profound implications. It suggests that supermassive black holes don't always remain at galactic centers. Some get ejected and wander. These wandering black holes are incredibly difficult to detect when quiet. The number of wandering supermassive black holes in the universe could be substantial. Every major galaxy merger creates the potential for a three-body ejection. Over cosmic history, millions of black holes might have been kicked out. These wanderers pose interesting observational challenges. A quiet black hole produces no light. It's invisible except through its gravitational influence. Detecting wandering black holes requires catching them during rare feeding events. The runaway also provides insights into black hole merger dynamics. The fact that such violent ejections occur means that binary black hole systems can transfer enormous energy to individual objects. Future observations will search for more runaway black holes. If they're common, it changes our census of where supermassive black holes actually live. Some are cosmic nomads traveling between the stars. Space between stars is vast and mostly empty. A black hole wandering through this darkness would go unnoticed for billions of years, unless it found something to eat. Astronomers just caught one in the act. The event designation marks a violent story. A star wandered too close to a black hole that wasn't where it should be. The black hole's gravity grabbed the star and began tearing it apart in a process astronomers call a tidal disruption event. Tidal forces are differences in gravitational pull. The side of the star closer to the black hole feels stronger gravity than the far side. When this difference exceeds the star's own gravity holding it together, the star gets stretched like taffy. Eventually, it rips apart. This process releases a spectacular burst of radiation. Gas from the shredded star heats to millions of degrees as it spirals inward. The resulting flare can briefly outshine the entire host galaxy. Optical telescopes on Earth detected this flare. The Hubble Space Telescope provided crucial data. High-resolution imaging showed the flare's location offset from the galaxy's center. The black hole sat thousands of light-years from where supermassive black holes normally reside. Chandra X-ray Observatory observations confirmed intense X-ray emission. The Very Large Array Radio Telescope detected radio waves. All the signatures matched a tidal disruption event happening in the wrong location. This marked the first time astronomers had clearly identified an offset tidal disruption event. Out of roughly 100 such events recorded, this was the only one not centered on its host galaxy. The black hole weighs roughly 1 million stellar masses. That's substantial, modest compared to the billions solar mass giants at many galactic centers. Its offset position suggests it was either ejected or formed separately. If it was ejected, some violent event in the galaxy's past kicked it out. This could have been a three-body interaction during a galaxy merger. Alternatively, gravitational wave emission during a black hole merger could have imparted a recoil kick. If it formed separately and never migrated to the center, it might be a remnant of a smaller galaxy that merged into the current one. During galaxy mergers, the smaller galaxy's black hole doesn't always make it to the new combined center. The tidal disruption itself provides a unique probe of the black hole's properties. By analyzing the light curve, how the brightness changes over time, astronomers can estimate the black hole's mass and spin. Wandering black holes could be more common than previously thought. They're just extraordinarily difficult to detect when quiet. Every major galaxy might contain several such wanderers, leftovers from past mergers. The discovery has motivated new searches. Astronomers are examining archival data from sky surveys, looking for other flares that occurred away from galactic centers. Computer algorithms can now flag potential offset events automatically. Each wandering black hole tells a story about its galaxy's violent past. They're refugees from gravitational battles, survivors of cosmic catastrophes. Among the thousands of galaxies observed by James Webb, a peculiar class stands out. They appear as tiny red dots in the infrared images, so faint and distant that previous telescopes missed them entirely. These little red dots are rewriting our understanding. The red color comes from extreme distance. As the universe expands, it stretches light traveling through space. The stretching shifts visible light into infrared wavelengths. The extreme redness of these dots indicates they're among the most distant objects ever observed. What makes them strange isn't just their distance, it's their properties. Detailed spectroscopy reveals that many little red dots contain supermassive black holes at their centers, monsters weighing millions to billions of stellar masses. The black holes are overmassive compared to their host galaxies. In typical galaxies, the black hole mass correlates tightly with the galaxy's total stellar mass. The ratio is roughly predictable. These little red dots break that correlation completely. Their black holes can outweigh all the stars in the galaxy combined. The discovery suggests black holes in the early universe grew faster than their host galaxies. They didn't wait for stars to form and enrich the gas. They raced ahead, establishing dominance early. This challenges the coevolution picture. Another puzzling feature is their abundance. James Webb has found hundreds of little red dots across different regions. They're a significant population, possibly a major channel through which supermassive black holes formed. The spectrum of these objects shows broad emission lines, indicating gas moving at thousands of miles per second near the black hole. This confirms active accretion. The black holes are feeding, growing, contributing to the overmassive nature observed. Interestingly, despite hosting massive black holes, many little red dots show relatively little star formation. Their galaxies aren't undergoing intense bursts of stellar birth. This seems contradictory, because the same gas that feeds black holes should also form stars. One possibility involves powerful winds and jets from the black hole. If the black hole feedback is strong enough, it could heat surrounding gas to temperatures too high for star formation. The gas remains available for the black hole to accrete, can't cool enough to collapse into stars. The little red dots might represent a specific phase in galaxy evolution. Perhaps all early galaxies go through a phase where the black hole grows faster than stars form. As the galaxy matures, this ratio normalizes. Testing this idea requires observing little red dots across different cosmic epochs. If they're more common in the earliest universe and gradually disappear as time progresses, it supports the idea of a transient phase. The discovery highlights how much we still don't know. These objects were completely unexpected. No model predicted such a large population of overmassive black holes in tiny galaxies. Each little red dot is a laboratory for studying extreme black hole growth. By analyzing their properties across cosmic time, astronomers are building a new picture. In the constellation Cygnus, astronomers discovered something that shouldn't exist according to conventional wisdom: a black hole with two stars orbiting around it, locked in a gravitational dance that challenges our understanding. Triple systems are inherently unstable. Having three massive objects gravitationally bound together creates chaotic dynamics. Orbits shift and change over time. Eventually, one object typically gets ejected. Triple systems, where all three components remain bound for millions of years, are exceedingly rare. The discovery came from careful analysis of stellar motions detected by the Gaia spacecraft. Gaia measures the positions and velocities of billions of stars with extraordinary precision. When scientists noticed two stars showing correlated motions, they investigated further. Calculating the invisible object's mass from the orbital dynamics yielded a surprising result. The unseen companion weighed at least 10 times our star's mass. Too massive to be a neutron star or white dwarf, it had to be a black hole. This configuration poses a problem for standard black hole formation scenarios. Typically, black holes form when massive stars explode as supernovae. Such explosions are violent, imparting significant kicks. These kicks usually disrupt any binary system, let alone a triple configuration. One possibility is direct collapse. If the original massive star collapsed into a black hole without a violent supernova explosion, it wouldn't receive a large kick. The system could remain gravitationally bound. The two companion stars show properties consistent with having formed together with the black hole's progenitor. They're similar in age and chemical composition. This suggests all three objects originated from the same molecular cloud. Studying this triple system provides insights into black hole formation mechanisms. If direct collapse can occur, it offers an alternative to supernova formation that might be relevant for the early universe. Direct collapse could produce more massive seed black holes. The system also tests our understanding of gravitational dynamics in multi-body systems. Detailed observations over years can track how the orbits evolve. Any deviations from predictions would indicate effects we haven't accounted for. Interestingly, the black hole appears to be accreting matter from one of its companion stars. The star is close enough that its outer atmosphere extends into the black hole's gravitational influence. Gas is being pulled away and spiraling toward the black hole. This accretion process is gentle compared to the violent feeding frenzies in the early universe. The black hole gains mass slowly. Yet, over billions of years, such slow accretion could significantly increase the black hole's mass. The discovery raises questions about how many triple systems might exist undetected. Finding even one suggests others are out there. Future surveys with increased sensitivity might reveal a population. For the study of early universe black holes, the key takeaway is that multiple formation pathways exist. Some come from supernovae, others might come from direct collapse. This diversity adds complexity. Could black holes exist before stars? The question sounds absurd. Stars form first, live their lives, and only then create black holes when they die. That's the sequence. Except possibly in the earliest moments, primordial black holes represent a radical idea. In the first fractions of a second after the Big Bang, the universe was extraordinarily dense and hot. Quantum fluctuations created tiny variations in density. Most of these fluctuations smoothed out. Some could have collapsed directly into black holes. These primordial black holes would form before atoms existed, before the first stars ignited, even before the cosmic dark age. They'd be the oldest structures in existence. If they survived to the present day, they'd be fossils from the Big Bang itself. The idea isn't new. Physicists proposed it decades ago. What's changed recently is the observational evidence suggesting primordial black holes might actually exist and might even explain the rapid growth of supermassive black holes. Here's the connection. If primordial black holes formed with masses ranging from hundreds to millions of stellar masses, they'd provide massive seeds for later growth. Instead of starting from stellar mass remnants, galaxy formation could begin with black holes already weighing thousands or millions of stellar masses. Evidence for primordial black holes remains circumstantial. Some researchers point to unexplained gravitational wave signals that might come from primordial black hole mergers. Others note that primordial black holes could constitute some or all of dark matter. The strongest argument against primordial black holes is the lack of direct detection. If they're common enough to solve the supermassive black hole problem, we should have detected them through various means. Surveys have set limits on how many primordial black holes of certain masses can exist. However, these limits aren't absolute. Primordial black holes might exist in a mass range that current surveys haven't probed thoroughly, or they might be clustered in specific regions rather than uniformly distributed. Recent theoretical work explored whether primordial black holes could seed the formation of supermassive black holes. The models show it's possible, only if the primordial black holes have specific properties and form in specific locations. Getting primordial black holes to galactic centers requires careful timing. They'd need to form in regions that later became sites of galaxy formation. The gravitational dynamics of early structure formation could naturally deliver primordial black holes to these special locations. If primordial black holes do exist and serve as seeds, they'd leave observable signatures. Their masses would be different from stellar mass black holes. Their spins might have particular distributions. Gravitational wave observations offer the best hope for detecting primordial black holes directly. When two black holes merge, they produce gravitational waves carrying information about their masses. Future detectors will be sensitive to mergers involving intermediate mass black holes. The primordial black hole hypothesis remains speculative. Most astronomers favor explanations involving stellar mass seeds or direct collapse. The idea persists because it's so elegant. Whether primordial black holes exist or not, the question illustrates how uncertain we remain about the universe's earliest moments. High above Earth's orbit, 3 spacecraft will form a triangle in space. Each side of this triangle will stretch 5 million miles. Between them, laser beams will track distances with precision beyond anything attempted before. This is the future mission, scheduled to launch in the mid-2030s. The mission is to detect gravitational waves from massive cosmic events. While ground-based detectors observe waves from stellar mass black hole mergers, this space observatory will observe signals from supermassive black holes millions to billions of stellar masses. For the mystery of early supermassive black holes, this represents a revolutionary tool. Gravitational waves travel through the universe essentially undisturbed. Unlike light, which can be absorbed by dust and gas, gravitational waves pass through matter almost unaffected. When two supermassive black holes merge, they produce gravitational wave signals that build over months or years before the final coalescence. The space detector will observe these signals from across the universe, potentially including mergers that occurred when the universe was less than 1 billion years old. The spin information is crucial. How fast a black hole rotates depends on its growth history. Black holes that grew through steady accretion naturally spin up to high rotation rates. Black holes that grew through multiple mergers with random orientations end up with lower spins. If early black holes typically have high spins, it suggests they grew primarily through gas accretion, possibly during extreme feeding episodes. If spins are lower and randomly distributed, mergers might have been the dominant growth channel. The rate of detections also matters. If the observatory observes many mergers of black holes in the 100 to 1,000 to million solar mass range, it supports the light seed scenario. If most mergers involve already massive black holes, it favors heavy seed or primordial scenarios. The mission will also probe the intermediate mass black hole population. These objects, weighing hundreds to thousands of stellar masses, represent the transitional stage. They're extremely rare in the modern universe and difficult to detect. Every intermediate mass black hole merger detected provides a data point for understanding growth pathways. Were these black holes always in this mass range? Or are they former stellar mass black holes that grew modestly before stalling? Beyond mergers, the detector might observe gravitational waves from extreme mass ratio in spirals. These occur when a small black hole or star spirals into a supermassive black hole. The gravitational wave signal maps out the space-time geometry around the supermassive black hole. If supermassive black holes in the early universe have unusual properties due to rapid growth, extreme mass ratio in spirals would reveal those differences. The gravitational wave signal encodes details about the black hole's mass, spin, and any deviations from general relativity. The mission's scientific return extends beyond black holes. It will observe gravitational waves from other exotic sources, like cosmic strings, phase transitions in the early universe, and possibly unknown phenomena. Preparing for the mission requires theoretical work now. Scientists are creating catalogues of predicted signals, developing analysis techniques, and building frameworks for interpreting observations. This represents humanity's next great leap in gravitational wave astronomy. The discoveries it will make could finally solve mysteries that have puzzled astronomers for decades. We've journeyed through violent feeding frenzies, magnetic field cathedrals, and runaway monsters racing through galaxies. Now it's time to connect these pieces into a coherent picture. The story begins in the chaotic early universe. The first stars formed from pristine hydrogen and helium, living fast and dying young. When they died, they left behind stellar mass black holes, the seeds of everything to come. These seeds weighed perhaps 10 to a few hundred stellar masses. Some regions of space saw different beginnings. Dense gas clouds collapsed directly without forming stars first, creating heavy seeds tens of thousands of stellar masses. Perhaps primordial black holes formed even earlier. Multiple pathways created a diverse population of seed black holes. Then came the feeding. Young galaxies were chaotic places, turbulent and violent. Dense streams of gas flowed along cosmic filaments, channeling fuel directly to galactic centers. When these streams arrived, they triggered feeding bursts. Black holes gorged themselves at rates exceeding the theoretical maximum. Magnetic fields enabled this rapid growth. They funneled gas inward, removed angular momentum, and shaped the accretion flow into geometries that allowed radiation to escape while gas continued falling. The fields launched powerful jets that carried away excess energy. During these extreme episodes, coronae persisted despite conditions that should have destroyed them. X-rays blazed forth, even as black holes violated fundamental limits. Radio jets shot into space. All three phenomena coexisted. The feeding bursts were temporary. After a few million years, the dense gas would be consumed, or stellar feedback would disrupt the flow. The black hole would enter a quiet phase. Over hundreds of millions of years, multiple bursts occurred, each adding mass until stellar mass seeds grew into monsters. Most seeds remained small, never catching the perfect alignment of conditions. Only a minority grew into the supermassive giants we observe. The universe ran a lottery, and a few black holes won big. As galaxies matured, conditions changed. Gas densities decreased, turbulence settled into organized rotation. The chaotic streams disappeared. By the time the universe reached a few billion years old, the era of rapid extreme growth had ended. This explains the timeline problem. We don't need black holes growing steadily for billions of years. We need explosive bursts in the early universe when conditions permitted what later became impossible. The missing years weren't really missing. They were compressed into brief periods. The The discoveries also solve the mass problem. Black holes could outweigh their host galaxies because they grew first and fastest. They dominated the central regions before significant stellar populations developed. The unified picture makes specific predictions. Early black holes should show signs of rapid past growth, including high spins from directed accretion. They should be surrounded by evidence of powerful past jets and winds. Observations are confirming these predictions. James Webb finds overmassive black holes in small galaxies. X-ray observatories detect bright coronae during extreme feeding. Radio telescopes see powerful jets from objects that shouldn't have them. We're witnessing a revolution in our understanding. Black holes aren't just passengers in galactic evolution. In the early universe, they were drivers, shaping their environments and growing through mechanisms that modern physics barely allows. The mysteries aren't fully solved. Questions remain about magnetic field origins, the exact triggers for feeding bursts, and the role of primordial black holes. Future observations will refine our picture further. What's clear is that the universe is more extreme, more violent, and more creative than we imagined. It found ways to build billion solar mass monsters in just a few 100 million years by exploiting brief windows when the normal rules relaxed. These black holes that make no sense to current physics are teaching us that our physics needs updating. The universe already solved this problem. We're just catching up to understanding how.